So welcome to the second lecture of Biology 107, everybody. So today we're going to be looking at the chemical basis of life. So as you all probably know, chemistry is very related to biology. So today we're going to be looking at some basic chemistry so we can get an idea of how that functions in life. So normally when I give this lecture in person, I like to show this picture right here. So I'll give you a couple of seconds to look it over. So I want you to tell me, what's the joke here? Where does biology or biologists fall in this picture? And what do biologists need to know and study in regards to chemistry? So again, a little question is going to pop up in a second, and it's going to give you a chance to answer these questions. So I won't beat a dead horse here since I think the joke is pretty obvious. But essentially the point of this picture is to show that as biologists, we need to understand chemistry, physics, and math to be good scientists. So today we're specifically going to be focusing on the chemistry part of that. If you go on to take more advanced biology, you'll probably deal with physics and math. But today, really the most important part is that we understand the chemistry of life. So to go back to sort of a graphical syllabus that I showed at the end of the first lecture, again, we're starting at the very bottom of the hierarchy of life. We're starting with atoms and molecules. And here they use an example of a molecule of DNA. So what exactly is chemistry? So as you probably know from high school or other classes you've taken, chemicals make up our body, our world, and all physical objects. So something like the desk that your laptop is sitting on is made up of chemicals. Your body is made up of chemicals. The food you ate an hour before you watched this lecture is made up of chemicals. Essentially anything that's physical is made up of chemicals. In chemistry, which is the field that studies chemicals, specifically studies how these chemicals interact. Also, as you probably know, chemicals are made up of atoms. And atoms are the smallest whole unit of chemicals. So these are things like sodium, silicone, carbon. These are all examples of different types of atoms. And these are the smallest whole units of chemicals. And generally, they are not broken into anything smaller than this. If you ever go on to study subatomic physics, you'll learn this is not exactly true. You can actually break up atoms into smaller things. But for the purposes of general biology, we're not really going to go into this. So we're going to say that atoms are the smallest whole unit of chemicals. And again, everything physical is made up of atoms. So now that we've talked about what chemistry is, let's talk about what an atom is. So the example we're going to use here is of helium. Helium you can think of being that colorless, odorless gas that fills party balloons. So the balloons you see at birthday parties, weddings, and things like that. So that's the gas that fills those and makes them float in the air. So here are 4 different pictures of helium atoms. So they're all trying to represent exactly the same thing, or they're representing helium in slightly different ways. So all 4 of these things are helium atoms. So there are 2 major parts of an atom. There's this center part called the nucleus. And the outer part, usually called the electron cloud. So again, 2 major parts, the nucleus and the electron cloud that is surrounding the nucleus. So here again is the electron cloud. Here we got the nucleus. Nucleus again, electron cloud on the outside. So take a second here and tell me what's going on with the nucleus in these pictures. So again, the nucleus is the center part right here. And specifically, I would focus on pictures 1, 2, and 4. So I'll number these. So 1, 2, and 4 are really the ones you want to describe. So tell me what's going on with the nucleus. So some of you may be having flashbacks to chemistry you took in high school or early in your college career, but you may remember that the nucleus is made up of two major components. The first component is protons, and the second one is neutrons. So looking specifically at picture number 2, in red we have protons, and in green we have neutrons. So those are the two major components that make up the nucleus. However, there's a third component that makes up atoms, and those are the electrons. So electrons themselves can be found in the electron cloud, so they're not part of the nucleus, they're outside of the nucleus. So again, three major components: protons, neutrons, and electrons. So in the next slide, we're going to look at these three things and sort of organize them in this diagram right here. So again, we have atoms at the very top, and atoms are made up of three major parts. So you have the nucleus in the center, and then we have electrons on the outside. The nucleus can further be split into protons, and neutrons. So atoms are made up of protons, neutrons, and electrons, and the protons and neutrons are found in the nucleus of the atom. So these three things, protons, neutrons, and electrons, the fancy word for them are subatomic particles. So a proton is a subatomic particle, a neutron is a subatomic particle, an electron is a subatomic particle. So they're all below the level of an atom, which is why they have this prefix right here, sub. So here again, we're going to have another question pop up. In this question, I want you to compare the size of the nucleus to the size of the electrons. And what do you notice in regard to the relative size of these two things? So the relative size of the nucleus to the relative size of the electrons. So most of you probably said the nucleus was much larger than the electrons, and that's absolutely correct. So that's a good observation. So if we look at the helium nucleus right here, that is much larger than the helium electrons on the outside. Looking at the other picture, we can see that the nucleus is also much larger than the electrons. So from this information, we can actually infer or learn something very important about electrons, protons, and neutrons, and that's specifically that electrons barely weigh anything. So atoms get their mass, a mass you can think of being similar to weight in a way, from the nucleus. So electrons, again, barely weigh anything, but protons and neutrons do have a significant amount of weight. And specifically, we're going to say that each proton and neutron weighs 1 gram, or has a mass of 1 gram. So 1 proton equals 1 gram, and 1 neutron equals 1 gram. So something like this helium atom right here, it weighs 4 grams. And I've also put a star at the end of the statement. So if you go on to more advanced chemistry, you'll learn that the statement of protons and neutrons equaling 1 gram each is not exactly correct. But for general biology, we're going to go with a reductionist approach and make life easier by saying that protons and neutrons equal 1 gram. So please do be careful if you take this information to other chemistry classes, since this isn't 100% correct. So let's go back to those 4 pictures I showed you at the beginning of the lecture. We're going to look a little bit more closely at them. So here again in red we have protons. Green we have neutrons. In yellow we have electrons. So I want you to look at the symbols for each of these. So notice the electrons have this minus sign, and protons have a plus sign. And I want you to tell me what you think these symbols mean. So as you probably guessed or knew from previous chemistry classes, subatomic particles have charges. So those plus and minus signs were the charges of the different subatomic particles. So you can think of charges almost being like a battery. So your standard AA battery has a positive end and a negative end to indicate the charges of the battery. So very similar idea in atoms. So there are protons, electrons, and neutrons. So remember, those are the three subatomic particles that make up atoms. Protons have positive charges, and they get the plus sign. A way that I like to think of this is pro. So you can think of something like a professional. Pro usually means good. So good, positive. So that's the way I usually remember it. Pro, professional, good, positive. Electrons have a negative charge, so they get a negative sign. You can think of electrons being similar to the word electric or electricity, which is usually bad. You don't want to stick your finger in a socket or something like that and get shocked. So electric equals bad, and bad equals negative. So those are some good ways to remember which is positive, which is negative. Neutrons, I think, is pretty straightforward. So neutrons don't have a symbol, but you can think of nu being the same prefix as in neutral. So neutrons are neutral, electrons are negative, and protons are positive. And also remember that opposites attract. So a positive proton is attracted to a negative electron. So atoms make up everything we see in life. So remember, everything that's physical is made up of atoms. And there are lots of different types of atoms that we can find in the universe. So something like sand is made up of two different types of atoms, silicon and oxygen. Something like sugar is made up of hydrogen atoms, carbon atoms, and oxygen atoms. And so on and so on. You can see at this table all the different types of atoms that make up the universe. An interesting fact is that 96% of the human body is made up of only 4 different types of atoms: hydrogen, oxygen, nitrogen, carbon. So these 4 different types of atoms make up 96% of the human body. So the fancy word for different types of atoms is elements. So here we have 25 different elements in this table. We have trace elements, specifically elements that are found in trace quantities in the human body. So these are things like boron, chromium, cobalt, copper, fluorine, and so on and so on. So these are different types of atoms, or specifically different elements. Again, we have oxygen, carbon, hydrogen, and nitrogen making up 96.3% of the human body. We'll talk about these symbols here, but essentially this is shorthand for writing different types of elements. So instead of writing out oxygen, you can put the symbol O, and that tells all chemists and biologists they're talking about oxygen. So again, those 4 elements make up 96% of the human body. There are also other elements such as calcium, phosphorus, potassium, sulfur, and so on that are also very important in the human body, but don't make up as large a quantity as these 4 atoms or elements we discussed earlier. So essentially, this table shows all the elements that are found in the human body. And again, elements being a fancy word for different types of atoms. So again, we showed 25 different types of elements in the last table. But here we have what is called the periodic table of elements. So all of you have probably seen this at some point, either in chemistry or on television. So essentially, the periodic table of elements lists all the elements found in the universe. So it has things like hydrogen, all the way up to things like borium, hassium, and new elements that are still getting names. So actually, this table is a little bit outdated. So we actually have elements extending out to this area right now. And those are still being discovered. So this table is actually outdated, and maybe the one in your textbook is a little bit more up to date. But essentially the picture or big idea here is that the periodic table of elements shows all elements found in the universe. And so the periodic table of elements is probably the most useful tool for chemists and biologists who are studying chemistry. And that's because the periodic table of elements provides lots of useful information for doing chemistry. So here we sort of zoomed in on one of the squares, specifically carbon. So if we go back to the previous slide, we've zoomed in on this square right here. So essentially each square of the periodic table is a different element. And here we're looking at carbon. So most tables will give you the full name of the element you're looking at. In this case, we're looking at carbon. It will also give you the abbreviated name or symbol. So in this case, carbon, the letter C is a shorthand way of writing that. It also tells us the atomic number. Please note that the atomic number is also the number of protons found inside the atom. So atomic number equals number of protons. And when we do math using these numbers, I'll show you why it's important that this is kept in mind. We also have the mass in grams of carbon. In this case, it weighs about 12.0107 grams. So just from one square of the periodic table, we can see all the information that we extracted from just that one square. Okay, so now let's go over a question. So the question is, how many protons does lithium have? You have four choices: A1, B2, C3, and D4. So you'll have to find lithium on the periodic table that I'm showing below, and you'll have to choose the correct answer to this question. So for this question right here, the correct answer is actually C, or 3 protons. So to answer this question, you really needed to do two things. First is you have to be able to find lithium on the periodic table. And the second is that you need to remember that atomic number equals a number of protons. So if you were able to do those two things, you were able to answer this question correctly. So to find lithium, you just have to look at the periodic table. So lithium is right here. So I'll circle it for you. So there are two numbers in the square. What you should note is that atomic numbers are always whole numbers. So in this case, the whole number is 3. We also have a second number, 6.941. So that is the atomic weight. And the whole number 3 is the atomic number. And again, you just use the fact that atomic number equals number of protons, and the correct answer here is C. So here's a little bit more tricky of a question. So if carbon has a mass of 13 grams, how many neutrons does it have? So again, you're going to have a question pop up. It's going to be multiple choice, so stick in your answer and see if you got the correct answer. So to answer this question, you need to refer back to some information we talked about earlier in the lecture. So remember, there are 3 types of subatomic particles: protons, neutrons, and electrons. A proton, a single proton equals 1 gram. A single neutron equals 1 gram. And remember, we're saying electrons don't weigh anything, so they weigh 0 grams. So essentially the math works out that if we just add protons plus neutrons together, this will give us the mass of the element or atom we're looking at. So for this question, we know the mass is 13 grams. So we have the number on the right side of this equation. And remember, the atomic number equals the number of protons. So we know there are 6 protons in carbon. So we'll leave our unknown as x. You can just rearrange this equation. So the answer is 13 minus 6, and that equals 7. So in this case, the correct answer is B. So there are 7 neutrons in this carbon that weighs 13 grams. So now I'm going to let you practice that one more time. Here we have sulfur, and it has an atomic mass of 35 grams. So this number right here shouldn't be 32, it should actually be 35. So using this information provided, answer this question and tell me how many neutrons there are in this atom of sulfur. So the math for this question is exactly the same as before. So protons plus neutrons equal mass. So essentially just have to plug and chug. So 35 equals number of protons, 16, plus x. So neutrons there, protons there, and 35 grams just came from the question. So just subtract 16 from both sides, and that gives us the correct answer C. There are 19 neutrons in an atom of sulfur. So next question, if sulfur has an atomic mass of 35 grams, how many protons does it have? So the point of this question is really just to see if you were still awake. So remember the atomic number, 16. Equals the number of protons. So it's very important that you remember that. So in this question, this atomic mass right here of 35 grams, essentially useless information. That's just to throw you off. So remember, atomic number always equals the number of protons. So in this case, the correct answer is A. There are 16 protons in sulfur. And again, you don't need to know this. All you do is just look at the atomic number, and you can figure out how many protons are in that atom. So we're going to expand on that. So I want you to take a look at the periodic table and tell me, do atomic numbers ever overlap? So that is, do we ever see 1 twice? Do we ever see 2 twice? 3 more than 1 time? So on and so on. So do we ever see numbers more than 1 time? So the answer here is that no, atomic numbers do not overlap. And you may have noticed that the periodic table is organized in increasing atomic number. So we start with hydrogen with 1, helium with 2, lithium with 3, beryllium with 4, and so on and so on. So essentially each atomic number is unique. So the thing to know here is that the element is determined by the atomic number. So essentially, remember atomic number equals the number of protons. So the element is determined by the number of protons. So I'll say that one more time. The element is determined by the number of protons. So if I ask you to find an element with 28 protons, that will always be nickel. So nickel will always have 28 protons. If I ask you for an element with 29 protons, that would be copper. So atomic numbers, or number of protons, never overlap. They're unique to each element. So protons are unique, but neutron numbers can differ between the same element. And the fancy word or technical term for this is isotopes. So here, again, the number of neutrons can vary, but the number of protons is constant. So example of isotopes are carbon-12 versus carbon-13. Both of these are carbon, but here the number of neutrons differ in these isotopes. And here I'll let you do this on your own, so a question's not going to come up. But if you have a periodic table available, you can answer the question of, if carbon has 12 protons, how many neutrons does each isotope have? And this also can be sometimes written as this form right here. So it has this superscript 12 or superscript 13 to represent carbon-13 or carbon-12. So I'm going to let you practice doing some calculations really quick. So here we have various isotopes of different elements. So we have things like carbon-12, hydrogen-1, phosphorus-31, fluorine-19, carbon-13. And I should say that this number right here equals the mass. So for something like phosphorus-31, the mass is 31 grams. So this is a nice table taken from the textbook publisher. So I want you to essentially fill it out. So I would take 5-10 minutes to do this. So you can pause the video and either write this in your notes, or you can print out the slide and fill out the table. So tell me the atomic number, the mass number, or just the mass, the number of protons, and the number of neutrons. For now, you can ignore this last column over here, which would be the number of electrons. So ignore that. On the slide, I've also posted a periodic table that's a little bit shortened, but that should help you answer all the questions for this table. So take about 5 or 10 minutes, either in your notes or print out this slide, fill out this table, and this will help you learn how to do math using different isotopes. Okay, so let's do some math. So let's erase all this first. And probably the easiest thing to do first is to calculate the mass number. And calculate is probably not the right word. The right word here would be just copy. So for carbon-12, the mass number is 12. It's already filled in for you. For hydrogen-1, it's just going to be 1. For fluorine-19, 19. And for carbon-13, 13. Next, let's do atomic number. So for carbon, let's look at the periodic table. That's 6. Hydrogen is 1. Phosphorus right here. That's 15. Fluorine, which is F. That's 9. And carbon, again, 6. So notice both isotopes of carbon have an atomic number of 6. So using the atomic number, we can figure out the number of protons. Notice that for the one that's already filled out. Here the number of protons for carbon-12 is 6. So remember, number of protons equals atomic number. And we can confirm that looking at phosphorus-31. The number of protons is 15, and the atomic number is 15. So for hydrogen, the number of protons is just 1. Fluorine, it's 9. And carbon-13, 6. So for number of neutrons, just remember that it's protons plus neutrons equal mass. In this case, since we don't have the number of neutrons, we just rearrange the equation. So it's mass minus protons equal neutrons. So you can ignore this equation on the right. So for hydrogen 1, we can see it's 1 minus 1 equals 0. For carbon-12, it has an atomic number of 6 for 6 protons and a mass of 12. So it's 12 minus 6 equals 6. So it has 6 neutrons. For phosphorus-31, it has atomic number of 15 and a mass number of 31. So it's 31 minus 15 equals 16. So there are 16 neutrons in phosphorus-31. For fluorine, it has a mass number of 19. So subtract out the atomic number or number of protons. That gives us 10 neutrons. For carbon-13, it has a mass number of 13, so subtract out the number of protons, and that gives us 7 neutrons. So again, looking at carbon-12 and 13 as examples, they have the same atomic numbers, both 6. They have the same number of protons, both 6. However, where they're different is in the number of neutrons. So carbon-12 has 6 neutrons, carbon-13 has 7 neutrons. So again, protein numbers are constant for the same element. However, between isotopes, the number of neutrons can differ. In this case, carbon-12 has 6 neutrons, carbon-13 has 7 neutrons. So now we're going to talk about some terminology. We're going to talk about things called compounds and molecules. So compounds are made up of 2 or more different types of elements. So something like this methane right here. This methane, it is a compound. So the key word here is different. So something like this oxygen right here, which is made up of 2 oxygen atoms. This is not a compound. So the word we would use to describe this oxygen is it's a molecule. So this is a molecule of oxygen. You can also say this methane is a molecule as well. So that methane is both a molecule and a compound. However, the oxygen, again, is only a molecule. It's not a compound. So both compounds and molecules are formed by chemical reactions. So here we have a chemical reaction. In this case, methane plus oxygen makes carbon dioxide and water. So a chemical equation or reaction looks almost like a mathematical equation. So you have plus signs to indicate that things are being added together. And then you have essentially the equivalent of an equal sign. You have an arrow pointing to show that the reaction has happened. So here we're adding methane CH4 plus O2 oxygen. We then have the arrow, and that shows that carbon dioxide plus water is produced. And everything, let me change colors really quickly. So everything to the left of the arrow, those are the reactants. Everything to the right of the arrow, those are the products. So reactants form products. So the reactants are methane and oxygen, and those form the products of carbon dioxide and water. So now we're going to talk about writing chemical formulas. So things like CO2, O2, the CH4 or methane we talked about, and also H2O. Those are all examples of chemical formulas. So the rules for writing a chemical formula is that the symbol for each element is only written once. So in these examples, carbon's only written once, oxygen's only written once, H is only written once, oxygen's only written once. So the symbol for each element only appears one time. This is then followed by the number of atoms per molecule. And specifically, that should be subscript. So those 2 is subscript, 2 is subscript, the 4 is subscript there, the 2 is subscript there. So looking at this example of C3H8, again, each element only appears once. Carbon appears once, hydrogen appears once, and each of those abbreviations are followed by the number of carbon atoms and hydrogen atoms per molecule. In this case, C3H8 has 3 carbon atoms and 8 hydrogen atoms per molecule. So now let's practice that. So let's imagine you have a molecule that has 14 carbons, or Cs, and 14 fluorines, Fs, per molecule. So what is the chemical formula of this molecule in this question? So for this question, the answer is D, C14F14. So remember, each symbol gets written once. So C gets written once, F gets written once. And now you just need to count the number of atoms per molecule. In this case, it's both 14 carbons and 14 fluorines. So it's C14, F14. So that's the correct answer. So now we've talked about compounds and molecules, but now let's talk about how those are held together. So what's holding the atoms of something like C14F14 together? And this is done through various types of bonds. And the 2 major types are covalent bonds and ionic bonds. So covalent bonds are often described as the sharing of electrons. And that's a very good example, or a good choice of words there. So in covalent bonds, you have sharing of electrons. So for something like methane, CH4, you have electrons being shared between the carbon and the 4 hydrogen atoms there. So that's a type of covalent bond. Then you have ionic bonds. So things like sodium chloride. This is table salt. It's a good example of a molecule that forms ionic bonds. So in this case, chlorine steals electrons from sodium. So you have the stealing of electrons as opposed to the sharing of electrons. So covalent bonds are sharing, ionic bonds are stealing. And I think both those words, sharing and stealing, are good choices of words to describe these 2 types of bonds. So now let's see an example of ionic bond. So this is from your textbook, and it's the same thing I mentioned earlier. So this is sodium chloride or table salt. And here you can see that stealing of electrons. So here we have this electron surrounding sodium. So Na, I should say, is sodium. And Cl is chlorine. So that chlorine atom steals an electron from sodium. You can see the arrow. So that chlorine atom steals an electron. And when that happens, you have the formation of sodium chloride. So this, again, is an ionic bond. So when you have this stealing of electrons, you form an ionic bond, and now this has formed sodium chloride. Next, we have covalent bonds. So whereas ionic bonds are stealing electrons, covalent bonds are sharing electrons. And so let's ignore this column right here and just look at the first three columns in this table. So as opposed again to stealing electrons, we're sharing electrons here. So you can see this H2 right here, there are 2 electrons being shared by these hydrogen atoms. For this O2 right here, they're sharing 4 electrons. For methane, we have 4 different covalent bonds. Here's 1 covalent bond, 2 covalent bonds, 3 covalent bonds, 4 covalent bonds. So that carbon is sharing 4 covalent bonds with 4 different hydrogen atoms. And lastly, we have water, so H2O, so 2 hydrogens, 1 oxygen. And again, that oxygen is sharing 2 different covalent bonds, each one with a separate hydrogen atom. So as opposed to drawing these dot diagrams, these are also called Lewis dot diagrams or models. The easier way to do this is just by drawing lines. So if you're sharing 2 electrons, that is a single bond, so you get a single line. If you're sharing 4 electrons, like as an oxygen, that's called a double bond. So you have 2 lines. For something like methane, which has 4 separate covalent bonds, you have 4 lines extending from the central carbon, and each of those represents a covalent bond between the carbon and the hydrogen. Similar to the methane, in water you have 2 separate covalent bonds linking the hydrogen to the oxygen. And we'll talk a little bit about what nonpolar covalent and polar covalent bonds are in the next slide. So the major point here is that covalent bonds are about sharing electrons, not stealing electrons. So I mentioned nonpolar covalent and polar covalent bonds. So this has to do with electronegativity. So polar covalent bonds are still considered covalent bonds, so still sharing electrons. But in the case of a polar covalent bond, those electrons are not shared equally. So you can imagine something like hydrogen fluoride, where you have a fluorine connected to the hydrogen. Fluorine likes electrons much more than hydrogen. So it actually turns out that electrons like to stick more around fluorine than they do around hydrogen. So fluorine is almost attracting or vacuuming away the electrons away from hydrogen and keeping them more around fluorine than it is around the hydrogen atom. And this is due to electronegativity. So fluorine is much more electronegative than hydrogen. So fluorine wants electrons more than hydrogen, and that's why it's able to keep the electrons more around itself than the hydrogen atom. So even though these atoms are sharing electrons, again, it's an unequal sharing of electrons, which makes it a polar covalent bond. And so a nonpolar covalent bond is the exact opposite of that. So that's the equal sharing of electrons. So for something like this methane right here, which is nonpolar covalent bonds, the electrons are shared equally between the carbon and the hydrogen atoms in this molecule. For something like water, which is a polar covalent bond, those electrons are hanging out more with oxygen than they are with the hydrogens. So oxygen is much more electronegative than hydrogen, so oxygen is keeping the electrons next to itself. So it actually turns out that fluorine is the most electronegative element. So I'll put fluorine here. So as you go left across the periodic table. As you go down the periodic table, it's less electronegative. So essentially left or down is less electronegative, and fluorine is the most electronegative. So fluorine wants the most electrons, or wants electrons more. So when you have two different atoms of two different electronegativities, you have a dipole moment formed. So I'll show you exactly what that means in the next slide. So here we have a dipole moment. So chlorine is more electronegative than hydrogen. Whoops. So again, chlorine is more electronegative than hydrogen, so it's keeping all those electrons around itself. So even though the chlorine and hydrogen are sharing a covalent bond, in this case a single covalent bond, those electrons that they're sharing are more around chlorine most of the time compared to hydrogen. So this forms a dipole moment. So this delta right here, this lowercase delta, this means slightly. So hydrogen is slightly positive and chlorine is slightly negative. So essentially what's happening again is that those electrons are floating around chlorine more than they're floating around hydrogen. And remember, electrons have a negative charge, so those electrons are floating around chlorine, which makes it slightly more negative than hydrogen. And this forms a dipole moment. And here we have an arrow indicating that chlorine is more electronegative and has more electrons hanging around it than hydrogen does. So now we're going to see how well you understood that. So here we have different molecules and hypothetical covalent bonds. So we have a hydrogen-hydrogen bond, a hydrogen-nitrogen bond, nitrogen-oxygen, and hydrogen-oxygen. So remember, fluorine is the most electronegative. As you go left, you become less electronegative. As you go down the periodic table, become less electronegative. So which of these would have the greatest dipole moment? Would hydrogen-hydrogen bonds have the greatest dipole moment? Would hydrogen-nitrogen bonds have the greatest dipole moment? So on and so on. So here again the question is, which of these would have the largest dipole moment? So essentially we're looking for elements with the biggest difference in electronegativity. So I'll just write out a little bit of the periodic table. So going across, we have carbon, nitrogen, oxygen, and then fluorine. So remember, fluorine is the most electronegative. I'll abbreviate electronegative as En. So fluorine is the most electronegative. And as we go left, we become less and less electronegative. So for all intensive purposes, carbon is about electronegative as hydrogen. So hydrogen and carbon have equal electronegativity. So let's just go through these lists of covalent bonds and see which one has the biggest difference in electronegativity between the elements. So for something like this hydrogen-hydrogen bond, this would be a good example of a non-polar covalent bond. So there would be no dipole moment here. So it's non-polar. So A is not a good answer here. Next, let's look at hydrogen and nitrogen. So they're very close to each other. So here we would have a slightly polar bond. So it would be a small dipole moment. So we can put maybe here. Next, we can look at nitrogen and oxygen. So nitrogen and oxygen are pretty close to each other. So again, we can put a maybe here. And lastly, let's look at hydrogen and oxygen. So if you look, there's actually a big difference in electronegativity. So we're skipping nitrogen. We're going for a hydrogen-oxygen bond. So in this case, it looks like D is the best answer. So here you would have the biggest difference in electronegativity and ensuring the strongest polar bond and the largest dipole moment. So D is the correct answer, hydrogen and oxygen. So let's look at this question of how many electrons does an atom have? So it's kind of hard to tell from these pictures of helium, the same ones we saw earlier. But you need to know that the number of electrons equals the number of protons. So we have 2 protons, and as a result, 2 electrons. And this is only true for a neutral atom. We'll talk about things called ions. And in the case of ions, the number of electrons change. So this is only true for neutral atoms where the number of electrons equals the number of protons. So based on the previous pictures of atoms, you probably saw that electrons form shells. So for something like sodium, you saw there were shells around it. So electrons essentially float or orbit around the nucleus. So you can imagine there are electrons floating around this sodium atom right here. So the rule or major rule here is that all atoms besides for hydrogen and helium want 8 electrons in their outermost shell. And the technical term for the outermost shell is the valence electrons. So electrons that occupy the outermost shell are called valence electrons. And here again I have the asterisk to show that if you take more advanced chemistry, you'll learn this isn't exactly true. So some atoms want more than 8 electrons, some want less. But for the purposes of general biology, we'll say that everything besides hydrogen and helium want 8 electrons in their valence shell. So now we're going to look at the rules for drawing these shells, specifically how the electrons fill them. So here we have essentially a periodic table. The middle part has been gotten rid of, but we have the left part and the right part connected. So you can see how various electrons fill shells. So going from something with hydrogen with 1 electron to helium with 2, you can see how the shells are filled, and then so on and so on with lithium, beryllium, boron, carbon, so on. So take a second to look at this slide right here and derive rules about how the electrons are filled. So specifically look at the first shell, their inner shell, and see what are the rules, what are the conditions for filling that shell. After you figure that out, look at the rules for filling the second shell, and look at the rules for filling the third shell. So what are the rules for filling the shells and drawing electrons? Okay, so let's look at the rules here. So let's clear this out really quick. So let's look at the innermost shell first. So notice in all of these, for beryllium, boron, carbon, nitrogen, so on, there is never more than 2 electrons in the first shell. So that's the rule for the first shell. So number 1, 2 electrons max in first shell. So that's our first rule for drawing electrons. There are never more than 2 electrons in the first shell. And you should also note that the first shell fills first, as you can imagine, so you go from the inside out. So for the second rule, notice that as the second shell fills up, 1, 2, 3, 4. Electrons are by themselves until you get past 4 electrons. Once you get past 4, they start pairing up again. So nitrogen, which has 5 electrons in its valence shell or outermost shell, 3 of those are unpaired and 1 is paired. So unpaired first, then paired. And specifically, the number is 4 unpaired, and then once you get after 4 electrons in the valence shell, they'll start pairing up. So for something like oxygen, which has 6 valence electrons, we have 2 unpaired and 2 paired. And again, going back to rule number 1, oxygen has 2 electrons in its first shell. And the last and final rule is we look at the valence electrons once you get past 8. So you have 2, 4, 6, 8. Once you get past that and go to sodium, you start a new shell. So here you have a third shell once you get past 8 in the valence electrons. So essentially shells in the second or third ring have 8 electrons max. So a little bit messy handwriting, but hopefully you get the idea. So the 3 rules are, for the first shell, you have 2 electrons max. You should always start from the inside or the first shell and go outwards. Rule number 2 is that you have unpaired electrons first, and then they pair. So 4 unpaired, once you get after 4 electrons, then you start pairing them up. And rule 3, for the second and third shells, you have 8 electrons max. So once that second shell is filled with 8 electrons, you start a third shell. So those are the rules for drawing electrons, specifically in these Lewis dot structures or Lewis dot diagrams. So this is a common exam question. So this is something you want to practice. Maybe you can blank out some of these squares and then try practice drawing them based on the number of protons. You can figure out how many electrons there are and figure out how to draw these various structures. But I think if you remember the rules, that's a good start to doing this on an exam or test. And so this information we already covered. So covalent bonds form between the valence or outermost electrons. So for something like this fluorine, only the valence electrons are reacting. So the electrons in the first shell aren't doing anything. It's only those valence or outermost electrons. And remember, covalent bonds are all about sharing, as opposed to ionic bonds, which are stealing. And you can share a various number of electrons. So you can share 2, you can share 4, and you can share 6. And respectively, these are called single, double, and triple bonds. So if you share 2 electrons, that's a single bond, 4 electrons double, and 6 is a triple bond. And again, molecules want 8 electrons in their valence shell. So 8 is a number you want to hit. So let's look at a familiar table that we saw earlier. So these are various molecules that have covalent bonds. So we can look at hydrogen. You can see that there are 2 electrons here. So remember, hydrogen and helium are the weird ones. So those just want 2 in their valence shell. So here we have a single bond between these hydrogen atoms. For O2 or oxygen, we have a double bond. Here we're sharing 4 electrons. And remember, we want 8 electrons in the valence shell. So here are 2, 4, 6, 8. So those are 8 electrons in the valence shell. We can go the other way around for the other atom of oxygen. So there are 2, 4 in the middle. There's 6, and there's 8. So 8 electrons for each of these oxygen atoms in their valence shell. And again, since they're sharing 4, we call this a double bond, so we get 2 slash lines between the O's. Next we have methane. And again, these are non-polar covalent bonds. So remember, carbon and hydrogen have equal electronegativity. So there's no dipole moment, so this is non-polar covalent. You can see that there are electrons shared between the carbon and the hydrogen. So for each of the hydrogen atoms, it has 2 electrons in its valence shell, which makes it happy. And for the carbon, there are 8 electrons in its valence shell total, which also makes it happy. So this is a stable molecule of methane. And lastly, we have water. Remember, this is a polar covalent bond. So oxygen is more electronegative than hydrogen, so it's pulling electrons towards itself, which makes this a polar covalent bond. And you can see there are electrons of hydrogen being shared with oxygen. There are 2 electrons in the hydrogen valence shell and 8 total in the oxygen. So 2, 4 between the hydrogen, 6 right there, and then 8 right there. So 8 electrons total in the valence shell of H2O. And again, since we're already looking at this table, I'll point out again that H2O is a polar covalent molecule. So if you look at the oxygen, it has a slightly negative charge, so it's a lowercase delta, and the hydrogens have a slightly positive charge. So again, the electrons are hanging out more with the oxygen, so this is more electronegative, and less with these hydrogen here. So that makes the oxygen slightly negative and the hydrogen molecules slightly positive. In the next lecture, this idea of polar covalent bonds is going to be very important, which is one of the reasons why I took some time to explain this here. So we'll learn more about these polar covalent bonds in water and why they're important in the next lecture. The next concept is ions. So we also touched briefly on this earlier in the lecture. So when an atom loses or gains an electron, as in ionic bonds, where they're stolen, so it's not shared but stolen, which is very important, ions are formed. So when chlorine steals an electron from sodium to make sodium chloride or table salt, ions are formed. In this case, we have sodium ions formed, and we have chloride ions formed. So again, when you have electrons stolen, you form ions. So whenever an ionic bond is formed, you have ions formed as well. And also an important note here is count the valence electrons. So notice that sodium has 2, 4, 6, 8. And chlorine has 2, 4, 6, 8 electrons total. So both of these have 8 electrons in their valence shells. So again, this is following the rule of 8. And so depending on whether an ion is lost, or sorry, not an ion, electron is lost or gained, this forms different types of ions. So there's a cation. The way I like to remember this is cats are positive. You can think of their nose as being a positive symbol. So this is when an electron is lost. anions, you can think of ants as being negative. They have antennae and legs that are negative. So anions or antions are negative. So you get a negative symbol, cations are positive. Just going back to the previous slide, we have sodium being a cation and chloride being an anion. So again, if you lose an electron, you become a cation. If you gain an electron, you become an anion. And this is all relative to the number of protons in the nucleus. Okay, so this is the very end of the lecture. So let's fill out this concept map really quickly. So this is going to see how well you understood this lecture today. So as I'm filling out, you can go along with me and see if you get the same answers. So looking here, we have an atom and it has 3 parts. So it has a positive charged proton. So remember, protons have a positive charge. They have neutral neutrons and negatively charged electrons. So remember that protons never differ between elements. So a sodium, I should say a lithium atom will always have 3 protons no matter what. So the only thing that can differ is the number of neutrons. And that number may differ in isotopes. Okay, so now let's look at C again. So electrons, number in the outer shell determines formation of chemical bonds. Electron transfer between atoms creates ions. So this is stealing, which means the other side of this concept map must be sharing. So let's look at E. So E is probably covalent bonds. So electron sharing creates covalent bonds. Unequal sharing creates polar covalent bonds. And equal sharing creates nonpolar covalent bonds. And we'll ignore this bottom part right here. So we'll save this for the next lecture when we talk about water. And so for F, the word is salts. So we won't go much into this, but essentially you can think of sodium chloride being a salt. Calcium chloride is also an example of a salt. So a salt is kind of a catch-all for something that's formed by ionic bonds. So lithium chloride, that's also a salt. So anything that's formed between, or anything I should say that's formed by ionic bonds is considered a salt. So it's things like sodium chloride, calcium chloride. So CaCl2, lithium chloride, potassium chloride are all examples of salts, which are formed by ionic bonds. So again, in the next lecture, we're going to be focusing on water. And this bottom part of this concept map will make a lot more sense once we talk about that. And again, this is going to have a lot to do with the fact that water is a polar covalent molecule.